a lot. I would like to first thank the organizers for the opportunity to speak here in this nice seminar and for your interest in our work. We actually, this is actually joint work with two collaborators from the University of Valencia, where I am now, with Salvador Moll and Marcos Solera. And we were wondering about how to use inverse mean curvature flow to model crystal growth. But somehow, in order that you can grasp what are the obstacles that we have to deal with to do such a definition, I need to give you some background about classical versus weak solutions of the inverse mean curvature flow, because somehow, if you go on at first headline of our work, we need to define a notion of even weaker weak solutions of the flow to be able to deal with a scenario of really milder regularity assumptions. So let me start with the very basics, and then we have like, so imagine a hypersurface. We have M0. Hypersurface that, well, a compact hypersurface enclosing a bounded domain, everything in Rn. And I can, any point, I can move it in the outward normal direction with velocity given by 1 over the mean curvature. And then classical solutions of the inverse mean curvature flow will be a family of immersions from a fixed M times some interval, 0t. Sorry that I get used to the blackboard. Takes a while. and then whose velocity is evolving exactly as I said. And then somehow what I mean by classical usually is two things, smooth and isotropic, because we somehow we are in Euclidean space, right, with the standard Euclidean metric, so everything is isotropic. And what you will expect is that, well, first thing is that you realize that H has to be strictly positive, otherwise you don't even have a solution. So this is a purely expanding flow, meaning that, well, what you expect is that after a while, this gets kind of expanding, and your MT, that is x of m comma t, is getting rounder. And that's exactly what happens. So if you, in the early 90s, it was proved by Gerhardt and Urbas independently. One moment. That if you have H strictly positive, and you assume that the boundary is smooth, and you need somehow an extra assumption, which is that it is star-shaped, then you prove that there exists a unique smooth solution. That will be empty as before. Then if it's the usual flow that is expanding all the time, then you will have somehow that the volume is increasing and will get out to infinity. So you really need to multiply by some factor e to the minus t over n minus 1, so that you get that the solution exists as t goes to infinity, to some kind of a round sphere. That's exactly the classical result, what you expect from a flow like this to happen, and that's the starting point. But well, as I said, we want to do it for crystals, right? So, and the first thing you need is to break the isotropy. So you really need to consider an anisotropic version of this flow, meaning that you need to define a norm in Rn, whichever one, no, not the Euclidean one, obviously, L1, norm, L infinity, your favorite by now. And then you have to modify the flow accordingly by considering, considering the anisotropic normal that's defined as the gradient f on the Euclidean normal. So the gradient of f, keep in mind that if f is the Euclidean norm, the gradient of f will be the identity divided by the f. So in this case will be nu divided by its norm, that is 1, so it's fine. And then h will be the corresponding divergence. So hf is the anisotropic mean curvature. Then
your norm is norm smooth or not necessarily?
No, I'm going to go in a minute to that hypothesis. So to get actually the result by Gerhardt and Urbas, it took like 27 years after that Sia got it. Well, having here the corresponding positive, and as you said, he had to assume extra that the norm is smooth outside of the origin, and furthermore, an ellipticity condition, so like the Hessian of f is strictly positive. And with that extra assumptions, Xia prove exactly the same result, but converts into the unit sphere of the polar norm that is called the Wolf shape. So the equivalent object with constant curvature in that new setting, right? So you have the classical smooth solutions, both in isotropic and anisotropic setting. But as soon as you want to remove any of these extra geometric conditions, like star-shapedness, you will realize that smooth solutions are not anymore the right thing. So, for instance, the easiest example is nothing fancy. You start with a very thin torus with the central circle so thin that the whole torus has positive mean curvature. So imagine that, well, that's the t equal to 0. And then you will let time evolve in this direction. And then what will happen with this torus is that it will puff out, and so it will expand, puffing the torus out, and until in the central ring, it develops some zero mean curvature, and hence the velocity of your flow will explode, and you will get a singularity. Because then the equation is not anymore defined, and then you cannot flow afterwards. So, and that's kind of a generic feature for singularities in inverse mean curvature flow. So each time your flow stops in finite time is because the infimum of the mean curvature over the hypersurface is mt converges to 0 as t goes to the singular time. That was proved by Smosik for R3 and Huisken and Ilmanen in general, meaning that, and that's the only obstacle So like the curvature going to zero is the only obstacle for the flow existing forever. But in that case, you cannot do anymore, and you want to flow beyond singularities. So somehow what the great idea of Huisken and Ilmanen by to introduce this kind of weak solutions of the inverse mean curvature flow is to remove the singularity and replace it by some jumping mechanism, meaning that I will consider this evolving hypersurfaces as the slices of some function in one dimension over. So let me, this will be like the graph of some function B. And in these slices, what will happen is that before developing zero mean curvature and getting some kind of a singularity, the solutions are allowed to jump to its outermost area minimizing hat. So what will happen here is that as soon as it is equally expensive to construct the torus than the like kind of the ellipsoid or like the outermost minimizing hull, the solution will jump instantaneously and then will continue evolving in a classical fashion. But as well, my picture may be not the best thing. I have one video to show it to you exactly what happens. So you see the torus that is growing till it will be 1 minute that it jumps to an ellipsoid and then keeps growing and getting rounder till it will end up in a round sphere. So after some rescaling. So and that's the main idea of Huisken and Ilmanen. So in this picture, I'm going to translate it to the equations, what this level set flow is, or the width of these weak solutions. So the idea is, as I said, you replace the empties now will be the boundaries of some sub-level sets, or otherwise will be the b equal constant t for some function. And now I'm going to derive the equation. So let me do it here if I have some space. So at any b at any point x of t will be equal to t. If I time derivatives, I will have 1 equal to gradient v multiplied by dt of x. But dt of x is nothing else than the flow equation, so that will be 8 divided by, no, that was the mean curvature flow, sorry. So we are in the inverse mean curvature flow, so that will be 1/8 times nu. If I multiply everything by 8, now I will get that 8 is equal gradient v times the unit normal. The unit normal will be gradient v divided by the norm. And hence, and hence I have gradient b to the square divided by gradient b. Then that's the norm of gradient b. Therefore, the weak inverse mean curvature flow translates to having the mean curvature 8, that's the divergence of the normal. So that will be divergence of gradient b divided by the norm equal to gradient b, the norm. That's the PDE, and look what's out. We have transformed a parabolic PDE into an elliptic one. And where this equation is defined is easier to see in the picture. So imagine that here everything happens, well, omega, forget about the torus, that downstairs here is your omega, your starting omega. No, I don't know what's going on. Sorry. That's your starting omega. And this is part of, this is within Rn. And everything happens out of omega, because imagine that here we have, I don't know, T1, and at T1 I will have some evolving guider. If I project downstairs, what we will have here will be all the ET1, that is all the values where B is smaller or equal than T1. So somehow what happens is that everything happens out of omega. Therefore, your PDE lives somehow in Rn minus omega bar, which is the region that I called omega E, exterior of omega, so that you remember. Then this PDE happens to be defined in the exterior of omega. And now notice that we had a parabolic initial value problem, and that will be turned out into an elliptic one, which is not initial value but boundary value. Because now your boundary condition is B equals 0 on the boundary of omega. And moreover, as you expect that everything spans out to infinity, you will expecting that B goes to infinity as X goes to infinity. And that are the two boundary conditions that, for people familiar with this vocabulary, that are the so-called proper solutions of the flow. So, and with that level set definition, with these boundary conditions, what can one prove? That was the results by Huisken and Ilmanen. In his classical seminal paper, where they use the flow to prove the Riemannian version of the Penrose inequality. You remove star safeness. You don't need any more that to have mean convexity, but obviously you sacrifice the smoothness of the solutions, and what you will get will be a function B, which is locally Lipschitz in this omega epsilon, or in this omega, in this exterior of omega. And well, that's the result of Huisken Ilmanen, so that you have you can grasp an idea of why of this the nature of this flow. Let me show you another video with so especially, well, if I got it. Especially for people that are familiar with mean curvature flow, which is a local flow. The inverse mean curvature flow, these level set solutions are sort of non-local in nature. And that's clear in this example of two spheres that are growing without knowing the existence of each other, but it arrives a moment where it is cheaper to build a catenoidal neck than letting them grow independently. And once they are joined by the catenoidal neck, it evolves like getting more and more rounded. So somehow that is a sign that the flow is non-local nature, because each of these two spheres cannot evolve all the time, ignoring the existence of the other one. So there are some global features that will affect the behavior of the flow. Now that we are talking about crystals, we have to wonder if this Huisken and Ilmanen result has a counterpart in the in the anisotropic setting, and the answer is yes. So you only have to modify accordingly this equation. So instead of gradient B, you will have the gradient F acting on this, and this gets removed. And here you will have, instead of the Euclidean norm, the F. And with that one, so, well, actually, I was talking all the time that this is an elliptic PDE. That's actually the one Laplacian of B, or the F1 Laplacian if you are in an anisotropic setting. So with that definition, we have the exact same result of Huisken and Ilmanen, but in this time that was proved by De La Pietra, Gavitone, and Chia, published 2 years ago. And then you have the same result. And that's fine, that's anisotropic, but we want to model crystal growth. And crystals in nature, nature, Capricious herself, the easiest one, so like a square form crystal, well, this hypothesis of smoothness of the boundary. So first thing that maybe you see, the most you can hope to assume here is to have Lipschitz, because these corners are typical in any crystal, the easiest one. And then what happens if you assume that the norm is smooth? Well, then you are imagining, if you assume that the norm is smooth, that the crystals in nature will evolve by rounding off the corners. Could you imagine that that's the real evolution in nature of a crystal? Well, I'm not going to ask you for any imagination game, because I'm going to show you that that's not the case. So let me show you some other movie. And so this one, so that you see it's a scientific one that's, well, now. And that from the Royal Institution of Sciences. Let me, in a minute, a square crystal will appear. And you see here, so it evolves like keeping the square shape more or less, and at any means keeping the corners, right? Therefore, we by all means, if we want to evolve a crystal, we are not allowed anymore to have any smoothness assumption on the norm. Let me stop that video now. So, and if we don't have any smoothness assumption, obviously, this other ellipticity condition does not even make any sense. So the question is, with almost no assumption in this landscape, so F is only a norm in Rn, and you have a set which boundary is Lipschitz, can we prove anything about inverse mean curvature flow? And well, the answer is, like, the quickest answer is yes, we can. And we means like our young work with Moll and Solera in a couple of papers in 2024 and 25. In which, in that situation, obviously, again, you remove almost all the assumptions. You have to sacrifice a little bit the regularity of the solution. So in this case, will be a function of bounded variation and in L infinity log. But your solution is not completely wild. So because the discontinuity set of the function B is negligible, in the sense that the n-1 Hausdorff measure of this is 0. And also that you will have a good control of B, because B lies between two explicit barriers. Meaning that you have two concrete functions that bound it from above and below, which allows you to argue with barrier and comparison arguments that make your life easier for the proofs. So that's our main result, which after that we make a little break for questions. I will give you details of how we managed to do that. But let me really point out that, well, the proof and the result is by far not piece of cake, because as you are not assuming any smoothness on F, the PDE does not even make sense, because what the hell is now gradient of F if F has no gradient? And also, if your function is of bounded variation, you don't even have also, it makes no sense at all to write the gradient of B. So somehow we depart from a point where we don't even know what's the PDE that governs the inverse mean curvature flow for crystals. And that's what we will have to give sense to that. And that's what I'm going to explain later on. But, well, somehow the moral of this, somehow most of us, we are geometers and usually live happily in smooth land. But reality out there is like highly non-regular, and we have to deal with that. And I will explain how in this particular problem we do for growing crystals under the inverse mean curvature flow. But before I enter in these technical details, so if you have any questions, I'm free to answer them.
Can you just repeat again for this particular instance when it has like cubical crystal? So what exactly your equation to what object? I must say I missed it a little bit.
Well, that I still
forget
didn't.
about everything just for this cube. Yeah. So what is your equation?
My equation, I can make you a further spoiler. What you will expect here will
equation,
be.
Well, first it's equation on the space where crystal lie, but now it's a function, right?
Yes. Yeah. Now it's a function, and then as you cannot write the gradient, then you will have the subdifferential of F. So you will have the divergence. Formally, the equation will look like the divergence of the subdifferential of F acting on the distributional derivative of a function that is of bounded variation. This thing here makes sense as a random measure.
But can you maybe characterize it, this whole solution with some variational principle, but you just minimize?
Yes, yeah. But that's the last part of the talk when I will tell you what's the variation principle behind that. So somehow the point is that so that you keep in mind, we have a very weak notion of solution and of equation in the sense of random measures. Let me finish writing the equation that will be f of dB. So that's an equality that makes sense as a random measure. So I will give you the exact definition of solution in a little while, but the nice thing is that then we recover all the properties that you will expect by being familiar in Huisken and Ilmanen. So the exact same minimization principle that Huisken has, we have it.
Okay, good.
So just need to wait till the end.
Okay, we'll wait, yeah.
Anything else?
I think it's very clear, and we're eager to see the rest.
Okay, then I go ahead. Well, let me finish the spoiler so that just in case I don't have time afterwards. So for people that really don't like having solutions that have so weak regularity, let me tell you that we have kind of some improvement in the regularity of the solutions if we add some extra assumption, that is what we call some interior bulk condition or interior ball condition. So, it's like in the Euclidean case, there is this rolling ball condition that you can roll a ball in the interior rolling through the boundary of your set. So here we will consider that our set is smoother if I can slide, because your ball now will be a square or something like that. So if I can slide a square of uniform size through all the interior boundary, then compare with that ball shape, with that square, that will be kind of smoother initial set. Imagine, for instance, a triangle cannot have this interior wolf condition for a square, because in the vertices you cannot stick in a square, but an L shape will have this condition. So if we have...
May I ask, excuse me, I wanted to ask something. Okay.
Okay. And then if you ask for that, then your solutions look much better because they are continuous and satisfy some Harnack inequality, in the sense that the oscillation of the solution is uniformly bounded in some uniform neighborhood. So if we ask a little bit more, we get more regularity of solutions. But as I won't have time to enter to the proof of this, but I wanted to so that you have the complete statement with all the situations.
My question is what? Because you are within convexity and your object convex.
No, we don't ask any convexity.
No, but because in your example in crystal, they're convex. And then they can be described also by support functions. So there might be some duality.
Yes. Yeah.
So can we see how it works with duality? Okay. What happens to dual equation? Then smoothness and flatness become complementary. Yeah.
Yeah. That's another way to, but we don't use that in the proof. But that you are right that one can transform it to the dual equation and see what's going on. Well, but of all the possible techniques that we can use, the one that has been pretty much successful is what is called Moser's trick. That is kind of in 2007. That's kind of, as I said, well, I made a spoiler in the page that was not saying spoilers about what the equation should look like. But in principle, we have no idea, right? So what is deserving the name of an isotropic inverse mean curvature flow will be what comes as the limit. So here you have a 1 Laplacian. So you will kind of approximate that by some kind of related P Laplacian equation. I'm going to write everything first in the isotropic setting, and then, because it's easier to grasp the ideas, and then I will modify that. So you will have kind of the P Laplacian, and that, so the idea of Moser is consider a related P Laplacian equation, and we'll write it in a minute, and then taking limits as P decreases to 1. So the P Laplacian is exactly the divergence of the norm of gradient V to the P minus 1, P minus 2, gradient B, and then equal to some kind of gradient term of natural growth, so that the equation is scaling invariant. So I will need here a power P. So if you study solutions of this P Laplacian equation, and then you make a change of variable, so Moser trick is in two steps. First, consider this equation, and then make a suitable change of variable that will be considered U equal to the e to the b. I need a negative exponent, so if p is bigger than 1, then 1 minus p. If you have this change of variable, turns out that the function u is p harmonic, meaning that, well, after the change of variable, this equation becomes, so the b's here are u's, but this side is 0. So you will have the P Laplacian equals 0. And the nice thing about that is that P harmonic functions have a nice variational interpretation, because then these u's are minimizers of the P capacity. I will recall in a minute when I start the sketch of the proof what is the P capacity. And hence, somehow the idea of Mozart is that step one, you study existence and characterize minimizers of the P capacity, and then you go back. So then you go back and do the change, take the limit, and what you got in the limit is a solution, is a level set solution of the inverse mean curvature flow. So we want to mimic this, this procedure for the anisotropic setting. So for the anisotropic setting, so you will have here an FP Laplacian. So here you will have F of this, then gradient F here, which kills 1 there. And then we will have F instead of the norm, that after the change of variable is still 0. So that's the way we want to do and construct and see what's going on in the limit. But as in the limit, we need to use all this machinery of sub-differentials and all that before starting with the sketch of the proof, and that you may start thinking that I am cracking nuts with a sledgehammer to convince you that all this machinery of sub-differentials and of all these technicalities is actually a need. Let me give you an example with the easiest, like the square crystal, and to convince you that I cannot evolve it under the inverse mean curvature flow, neither level set nor classical, neither using the standard Euclidean normal, nor this anisotropic one. So for that, I've got here the video we have seen at the beginning of the, well, at the beginning, some minutes ago, the video of the crystals evolving, and I have been drawing the ideal crystals out of that. So that is for, well, first, that squares are the Wolf shapes for the L1 norm. So F in this case is the one norm, so sum of the absolute values of the coordinates in the plane. And notice first that the Wolf shapes are actually the stable solutions of the flow, because even if we just start with something that looks smoother, as the solutions of Wolf shapes are solutions of the isoperimetric problem, so you minimize the one perimeter. Therefore, in this case, if I draw a line here, I'm getting smaller perimeter, and actually the one perimeter of this blue line is the same as this one, as the corner. So even if you start with the green smoother thing, the solution will jump instantaneously to the square. Therefore, that are clearly the stable configurations, and as we saw in the video, they should evolve as squares. So it is clear that in the corners, where the unit normal, the Euclidean unit normal, is not defined, but in the corners we need to have this evolution that are pushed this way so that this grows exactly as it is expected. And then for all the other points, here we will have like the gradient of B. In this case is 0, 1, and in these areas, the gradient is 1, 0. And you may think, well, there is only 4 points where the unit normal, the Euclidean one, is not defined. Let's use it in all the other places in the axis. But if you do that, then here in the corners, you will create a jump, and this jump will produce that this divergence here is a singular measure. And that cannot be a singular measure because we are claiming that the solution B has no jumps. So that's not the right way of evolving that crystal. So with the Euclidean normal, it doesn't work. Let's go to the anisotropic unit normal. Remember that we have it here, the gradient of f acting on nu. The gradient coincides with the subdifferential where things are smooth. So therefore the subdifferential here will be the sign of its component. So that will be He1 divided by absolute value, He2 divided by absolute value. Precisely on the edges, that is multi-valued. So that's not, so the gradient is not defined, it's where it is degenerate. So we can also not choose there in any of these points. We cannot choose the anisotropic unit normal. We have to instead choose an element on the subdifferential, so set in the subdifferential of f of gradient b. That's the corresponding thing that we had in the equation here. So we'll have set here. And what does it mean? As f is one homogeneous, that can be characterized as it's an element on the Wolf shape, so f0, the polar norm smaller or equal than 1, and then set times gradient b. If Cauchy inequality was true, that will be smaller or equal than the norm of each of these. But as the norm of set is smaller or equal than 1, I don't write it. But instead of smaller or equal, you get the best, the maximum value. You get equality. So that characterizes elements of the subdifferential. And if you are familiar with this terminology, what you need to define the flow here is to choose one of these sets, what is called a Kahn-Hoffman vector field. And but you have lots of choices because somehow this condition here is only telling you that the first coordinate of set, for instance, in these points, the first coordinate is 1, and for the second one, you have a choice between all the slopes between -1 and 1. So which one are you choosing? Well, actually, the right choice is to have a continuous interpolation between this vector and the ones in the corners with two goals. In order that there is not to avoid this jump here, we don't want this. We don't want a singular measure in our equation. And also because the divergence of this vector field you choose has to be constant, and you got it this way because Wolf shapes are the objects of mean curvature in your norm space. So the moral of that you keep in mind is that even with the easiest example, we can do anything with the traditional classical solutions. Weak or not, anisotropic or not, we really have to deal with subdifferentials instead of gradients. We have to deal with functions in BV. So I'm going to start with the strategy of the proof. Well, let me go to the ansatz to recall that the first step is to characterize the minimizers of the P capacity, and then go back. So first, that will be to characterize minimizers of the P capacity of like omega, the closure of omega. Let me remember what's the definition of that. First isotropic, and then I shift that. So what you do is kind of, you integrate over Rn, the p norm of u, pardon, sorry. And in which space? So you will consider the infimum of this integral for any u. Well, first thing that you will need here is that the gradient of u is in LP. Otherwise, your integral won't be defined. And actually, we are going to work with the closure of smooth functions with compact support under the norm, the LP norm for the gradient, and that's the so-called homogeneous Sobolev space, W1P of Rn, which can be characterized as those functions in Lpn divided by p minus n, so that the gradient is in Lp. So typically, you will call this exponent p star. And that space has the advantage that you have some Poincaré type inequalities that allow you to prove most of the estimates you need. So it's a crucial step in all the proofs. So you minimize in this space for functions that are bigger or equal than 1 in omega. But well, somehow on the minimizer, you will have equality. So you can either assume that u on the boundary is 1 and then integrate in the exterior of omega, because in the interior the gradient will be 0, and then consider here also the exterior of omega. So that's your functional. Obviously, if you want to have it anisotropic, just simply have here the F norm. And then, as we said before, by this Mozart trick, minimizers of the P capacity are P harmonic functions. So, well, in an anisotropic setting, so you will have here the P Laplacian. I'm not going to write again what it was. The P Laplacian of u equals 0 in omega epsilon, in omega exterior. And with boundary condition u restricted to the boundary, all these equalities are in the trace sense. That will be, remember that we made a change of variable. So B was 0 on the boundary. So now we will have 1. So this will be 1. And then u, as we have a negative exponent, if B goes to infinity, u will go to 0 as x goes to infinity. So that's the PDE problem you have to study to look for minimizers of the P capacity. And well, any analyst, when you see a PDE like that, you wonder about existence, uniqueness, and regularity, and make estimates to prove that. And the point is that so far the best result when we started this problem, the best result available was by Bianchini and Chiarolo in 2018 with some kind of extra technical hypothesis. So I'm telling you which ones. They have existence and uniqueness if you assume C2 alpha for the norm in Rn minus 0. Actually, assuming C2 alpha or C infinity is more or less the same. And some ellipticity condition, in this case, the Hessian of the P norm strictly positive. And also, as somebody was asking, they really needed convexity, convex domain with boundary, which is also more regular than a crystal, with regularity C2 alpha. So we generalize this result in several senses. So that's as this is the first step, this should be kind of in our first work, despite this is the second one published, but you know how this business goes. And we actually generalize it in several directions, in the sense that, well, as you may imagine, as before, we don't ask anything of regularity nor ellipticity of the norm, don't need that the domain is convex, and the only requirement for the boundary is that it is Lipschitz. And we get exactly the same existence and uniqueness result that they do. And we even work in the exterior domains or in omega bounded, which is a case of independent interest, and with generic boundary conditions. So a V that doesn't need to be constant. And how we prove like existence and uniqueness here is by kind of variational methods. So we defined an energy that will be some F here that will be defined in LP star of Rn to 0 infinity. That energy is basically the P capacity if we are able to integrate. So integral in omega in the exterior of omega of Fp gradient U. If U is in the Sobolev space, the uniform Sobolev space 1P of Rn, where we fix the value phi on omega and infinity otherwise. So that's your functional. So let me make some remarks that I think are important. So as this P norm, is coercive and convex, by applying the standard classical method of calculus of variations, there exists a solution. So we get existence if your domain is bounded, which in the case of the exterior of omega is not the case. But well, if in the case that it's bounded, we will have existence. And another thing to remark is that we will have, if we have strictly convex, then we will also have uniqueness. But with our assumption, so convexity of the F will make that your wolf shape is C1, which is not what we want. So actually, we have a problem to prove. So proving uniqueness is actually harder than expected. And I want to remark that we actually do have uniqueness. And let me make some parentheses here to tell you about the uniqueness, because I think that philosophically is nice what we do, because somehow the flow of ideas in all the papers I know that use Moser trick go in this direction. So you study, as we were doing, P harmonic functions, then undo the change and take the limit. But somehow, because of what I said, we were not able to prove in a first instance uniqueness of these minimizers. So only existence. But then when we were talking about, or we were starting the paper of inverse mean curvature flow, we came out with Huisken and Ilmanen's proof of uniqueness, which was really inspiring for us. In a completely different setting and mixed with other techniques, we have managed to adapt that technique to prove uniqueness here. And then it's where you say, what if you try downstairs? And actually uniqueness was working also there. And then you can go back and prove uniqueness of the minimizers here. So I'm saying that somehow, so far I know, our paper is the first time where the flow of information helps from the inverse mean curvature flow to P harmonic functions and not the other way around. So that's, as I find it nice, I wanted to highlight this part. So let me keep with the sketch of the proof. So if we have that U is a minimizer, then standard fact for people working with non-smooth things is that U is a minimizer if the zero belongs to the subdifferential of F of U. That's a completely standard fact. But, well, as I said, my life used to be smooth before I met some of my collaborators. And I even if it's elementary, I want to show you that with a quick picture. So you have here, I don't know, going this, there. So if we have a convex function and you have some of a smooth point, then you have the tangent slope, that's no problem. But if you have a non-smooth point, then all the possible slopes belong to the subdifferential. And if you have a global minimum, you see that the zero belongs to the subdifferential. But here you see, for instance, a point that is not smooth, and it's only a local minimum, it's not a global minimum, and then the zero is not, the zero slope does not belong to the subdifferential that will be here in orange. So that's kind of a standard fact. But the point here is that we need to, somehow we need to characterize what the subdifferential of this function is in order to have an idea of, in our so weak regularity setting, what's the equation look like? That's what's this system looking like. So, and that's our first result. So somehow we prove that an element W belongs to the subdifferential. So that's a theorem. I'm going to state it or not to prove anything. If you can find a set that will be in L infinity of the exterior of omega in Rn, which is in the subdifferential with the characterization I have given a while ago when we were looking at the, sorry, that's you. When we were looking at the evolution of the square crystal. And then you find this set such that W is minus the divergence of P f to the P minus 1 of the gradient times Z. Weakly. Weakly means that if you multiply by a test function and integrate the typical integration by parts formula holds. So somehow, if you want to have a zero here, if you want to have a zero, like the P doesn't matter. So that's formally the equation you will expect to find. So let me go back. If you have here, we have F to the P minus 1 of the gradient. That's what I got there. And instead of the gradient of F, I get an element of the subdifferential. So that's exactly formally what we should expect to have. And then second thing we need to prove, so second step, I'm not going to give any details of the proof because, well, I have been talking for an hour now, but so let me give a quick sketch and then recover the properties of the solutions. So the second thing is to have a comparison principle that will help to have uniqueness barriers that will give the regularity of your solution. So comparison principle means if you have here two solutions, so for I equal 1 or 2 and 2 boundary conditions. So if phi1 smaller or equal than phi2 on the boundary, then that propagates on the whole solution. So, and that is helping to get uniqueness and to get barrier estimates to have that you have existence and uniqueness of solutions in W, in the W1P of Rn, so in the homogeneous Sobolev space. Let me point out that as a bonus result, by refining these comparison principles, I can afterwards, if you are interested, I can give you an idea of how the proof works. The point is that if I assume this interior Moll condition or interior Wolf condition, I get, by refining these comparison principles, even more regularity. I will get that the minimizers are Lipschitz functions. But as this is not, this is an extra result, not entering the proof, let me skip that. And after you got the comparison principle and you actually get existence and uniqueness of all the problems in our ansatz, somehow what you need is to undo the change of variable and produce further estimates that pass to a limit to see what equation you get in the limit. So let me go back to the ansatz. What we have done is that for each p bigger than 1, we have constructed UP, a minimizer of the P capacity. Then we have the UP here. And then you undo the change, and you will get here a sequence BP for P bigger than 1 in of solutions of this P Laplacian equation, and then you will need to have the estimates that allow to pass to the limit here. Even if you pass to the limit here, you only will have some set whose divergence is a measure, but you still have to say what does it mean that this set is a solution of the anisotropic inverse mean curvature flow, and check that it really is. What you get in the limit satisfies sort of an equation. So let me give you the precise notion of solution here in the sketch. So after undoing the change, I have B bigger or equal than 0. That's a solution of the inverse mean curvature flow, or the anisotropic, crystalline, whatever you want to call this, if I can find a set in L infinity as before, with which is in the Wolf shape. And now, so that the divergence is a bounded random measure, and satisfies the equation in some sense. So the equation has to be that this divergence of set is, as was written before, f of dB. And more or less, you don't have to mimic that formally this set is in the subdifferential, so that you have an equality like this equal to set times dB. Like the semicolons is because this is in the sense of something called Ancelotti pairings, that if you are not familiar, forget what is said. It's some technicality that allows you to have some green formula in a weak sense, and that's for BB functions. And then you have to verify the boundary conditions for your solution. That will be that B equals to 0 almost everywhere in the Hn minus 1 measure on the boundary of omega, and then that you have a proper solution, so B going to infinity as X goes to infinity. Okay, so this step of proving estimates and checking that what you get to the limit satisfies all these things. Well, if I didn't check badly yesterday, it's like 5 pages of the paper, so it's not a piece of cake. But at this point of the talk, some people will be thinking, what the hell of a notion of solution is that? So you have an equation. So if even in the friendliest scenario of your minds, you will be thinking of that I have a weird equation that makes sense as a random measures, and this notion of solution. So what to do with that? So surprisingly enough, so I want to finish the talk by showing that all the first that with this notion, we are able to construct explicit examples of solutions, and that we recover all the nice classical geometric properties of solutions that you will expect from being familiar from Huisken and Ilmanen proof. So, for instance, you will have that B has a variational definition, exactly the I don't have time to give details, but exactly the one that you will get from Huisken and Ilmanen's paper. And also that you have a geometric definition for solutions of the flow, in the sense that sub-level sets that will be, so ET, that will be the sets of B smaller than T, and GT with the equality non-strict, so smaller or equal than T. That sub-level sets also are minimum, so of some functional. Then these sets, by B being a function of bounded variation, that are of finite perimeter for almost every T. That's trivial for the definition of bounded variation, but we prove that that happens for all T. And to understand the next properties, let me show you an example. If I can select the video. So we have our starting omega are 3 squares that and the norm is the one norm, and they will grow independently as squares, as we have seen before, not knowing the existence of each other, till it arrives sometimes where sometime t, where the perimeter of the three triangles is equally cheap, so has the same perimeter as if I consider the bigger square surrounding these three, that will be GT. And in that case, the solution will immediately jump to this GT, and then we will have some flattening. So the solution B will be constant in all this area. So the level set equation will be completely singular there. And once I got this jump, then this square is again a wolf shape and will flow as we are expecting. So that's not only a simulation and an intuitive example. We have exactly who is B, who is Z. So we have computed completely explicitly the solution. So let me put it another way. So that, and then I stop it in a place where you can see there. Okay, so as in this example, in general, the perimeter is continuous. The F perimeter of ET coincides with the one of GT, so behaves in a continuous way. The F perimeter is simply integrating on the reduced boundary, say of ET, F of the unit normal with respect to the n-1 Hausdorff measure. Another property that you have by Huisken Ilmanen is that exponential growth of the perimeter. So if you rescale by e to the minus t, any of these perimeters is constant. And you get also minimizing Hall properties of the solutions. Meaning that this set ET is some kind of minimal compared to competitors coming from the outside. So minimizes perimeter for all the subsets containing it and containing the original omega. And about GT is is strictly outward minimizing, meaning that among all the anisotropic perimeter minimizers or envelopes of ET, GT is the one that maximizes the Lebesgue measure. So somehow, when we started this project, and we wonder, can we make the inverse mirror curvature flow work for crystals in this so mild regularity scenario? So if we were in that moment making a wish list of things that you will like to prove of the solutions, that will be exactly the list of things, because that's exactly what appears in Huisken and Ilmanen's paper. And well, at this stage, well, I'm happy to see that we got proof all of them. Obviously, with more work, because our notion of solution is harder and it's in a geometric measure setting. So for us, it's like 12 proofs instead of half a page. But we get all that, so it's kind of what else would you dream of? And but if I say it so, looks like a dead end, and it's not the point. So since at some point it's kind of the beginning of something new, because we set all the foundations to be able to treat inverse mean curvature flow in scenarios of weaker regularity. And we all know of the power of inverse mean curvature flow to produce nice geometric inequalities, like the Penrose Riemannian inequality, which are meaningful even in the physical setting. So that's kind of our work kind of opens the door to look for such applications, or to revise all these inequalities coming from inverse mean curvature flow, but with much weaker assumptions. And but now I'm dreaming loud, so let me go back to Earth. And thank you for your attention, and I'm open to all the questions you may have.